So now let us see on how we can be able to express the relationship that exists between the dog as well as the angular acceleration. Let's say we have a circle. Let me have it in this way. Let's say we have a circle of, let's say, a center given as that. And assuming that we have an object and that is moving along the circumference of the circle with, let's say, a radius given as r. And let's say the object is of mass given as m. And it is moving along the circumference of the circle. And of course, using according to the rotational kinematics, that is according to the circular motion concept. And you should remember that at each and every point along the circumference of the circle, the object is said to have a tangential speed, and which is given as a vt. So at each and every point, tangential speed changes the direction. So whenever the object is, let's say, at this position, tangential speed points in this direction. And whenever the object is moving is at this point, tangential speed points in this direction. Likewise, at each and every point, the object is said to change its tangential velocity or speed. Now, since the object is changing actually the direction of the tangential speed, then the object is said to be accelerating tangentially. Then the object is said to be accelerating tangentially. Now, let's say the force responsible for the acceleration is given as F, because according to the Newton's second law of motion, you should have to expect that whenever there is a change in actually acceleration, then always the force has to be there responsible for that kind of actually a case. So now in this case, the force responsible for the actually a tangential acceleration, it is given as actually F, and which is always perpendicular to the actually radius of the circle in that case. Now, according to the Newton's second law of motion, how should we have that actually tangential acceleration? Now, we know that the force responsible for the acceleration is given as the mass times acceleration. Now, since the force is actually tangential to the radius, or the force is tangential to the actually a circle in which the object is moving along, then this acceleration, it is the tangential acceleration. Now have it as F is equal to mass times the tangential acceleration. Now if we think of making the tangential acceleration as the subject, we'll have the forces actually, we'll have the acceleration divided by the actually mass. So using the concept of the rotational kinematics, you should know that the tangential acceleration is given as the angular acceleration times the radius. So what is the angular acceleration? We'll have it as, now the angular acceleration is given as the tangential acceleration divided by the radius, in that way. Then I just have to substitute. Now we just have to substitute this. That is, we'll substitute for actually a tangential acceleration, and with that, so which means we'll have the angular acceleration being given as force of mass, and overall divided by should be radius, that is of 1. Now we have the angular acceleration being given as force of mass, and the times 1 over r in that way. Then what will go up next? Now what is happening now is that we'll have it as the angular acceleration being given as the force divided by mass times radius. Then according to the principle behind the algebra, if let's say we have 5 over m, you know this is the same as having it as, let's say, 5x over 5 should be 5x divided by mx. That is if we multiply numerator as well as the denominator by x. It is the same as that. Nothing changes. So if we do the same by multiplying this one, by multiplying the numerator by radius and also the denominator by radius, then what we have is the force times radius divided by mass times radius square. This is what we have as the actually angular acceleration in that way. So we have the angular acceleration being given as this. But you know that always the force is perpendicular to the actually radius. So what is the force times the perpendicular distance? Now we have it as a torque. So have angular acceleration being given as actually torque divided by what is the mass times radius actually square. A mass times radius square is said to be the moment of inertia, and which is symbolized as capital I. So moment of inertia, it is given as the mass times radius square, which is said to be the mass in motion. So which means now we have the new formula for the angular acceleration, which is given as the torque divided by the actual moment of inertia. On the same case, we have also this formula for a torque, which is given as the angular acceleration times the moment of inertia in this case. Now, if we have the system of several actual torque, then what will happen is that we'll have the summation of the torque being given as angular acceleration times the moment of inertia. This is what you call the Newton's actually a second law of rotation motion. You should have to understand. And it is much in line with the Newton's second law of motion, which is given as the mass times acceleration. And the acceleration itself, it is now for this case acceleration, it is actually angular acceleration, while this one it is the linear acceleration. And of which, if we have the system of several forces, then we'll have the summation forces is equal to mass times acceleration. So that's how we can get it up to. So the value of the angular acceleration can be obtained using different formulas from the way we discussed about the rotation kinematics. So let's see some of the typical examples you have to expect. Now let's say this is the question. A right rope wrapped around a disc-shaped buoy is pulled tangentially with a force of, now we have the force, that is 0.51 newtons. Define the angular acceleration, which is actually that is, and given that the mass, is 2.4 kgs, and always the mass has to be in kgs, and the radius of the radius of the buoy should be the radius of the buoy is given as, that is 0.13. Now how should we have the angular acceleration if this is the case? Now the angular acceleration will be given using the formula, that is using the formula for the torque, and which is given as angular acceleration is given as a torque divided by the moment of inertia, of which the moment of inertia is given as I is equal to m actual square, and the torque is given as force times radius. So you'll be able to have the angular acceleration in that case. So let's say this is the question. A wind turbine has a radius of 37 meters. That is the radius. 37 meters. And a moment of inertia that is 80 kgs should be a meter square. Should be not bare, but should be a meter square. That should be a meter square. That is a meter square. That is the moment of inertia. That's its basic unit. That is a moment of inertia. Mind you, it is mass in motion. That is 80 kgs meter square. And rotates with an initial angular speed. That is initial omega. That is be given as, should be initial. I usually use it as omega I corresponds to the initial, like that, which is given in radians, which is given in radians per second. And when the wind speed increases, the turbine experiences the net torque. Now we have a torque which is given as 16,000 Newton meter. Now, how many rotations? Now we are looking for the angular displacement. Now we are looking for the angular displacement, which is given as theta. But that particular angular displacement should be expressed in terms of revolutions. Now, how many revolutions does it take for the angular speed to increase? Now we have the final angular speed, which is omega f. That is given as 1.8. Now, how should we have this? Now, first of all, let me just have to eliminate the first part. So we have the actually a radius which is given as 37 meters, and we have the moment of inertia which is given as 80,000 in that case, and we have the final angular speed which is given as 1.8, and we have the initial which is given as 1.1, and also we have a torque which is given as 16,000. In that way, we are looking for the angular displacement in terms of revolutions. Now, how should you have it? Now, using the equations of the rotation kinematics, which actual formula should we use to have the angular displacement? By the way, we use the formula which is given as the angular velocity square, and is equal to the initial angular velocity square plus 2 angular displacement should be plus 2 angular acceleration times the angular displacement. So which means we are looking for the angular displacement, of which we are going to have the angular acceleration using the a moment of inertia as well as the torque. You have the angular acceleration using that. Then at the end of the day, we're going to solve for the angular displacement. Upon having the angular displacement, then you convert it to revolutions. So that's how you are going to have it in that way. Then the question part B says, what is the linear speed of the tips of the turbine blades 27 seconds after the acceleration begins? So now we are looking for the actual linear speed. Now we have been given the time x given as 27 degrees, and we are looking for the linear speed given as that one. How should we have the linear speed? Now first of all, we are going to have the a final angular speed with 27 seconds. Then upon having this one, that's when we're going to have the linear speed, and using the formula that is actually a linear speed Vt is equal to radius times the angular speed. Now in this case, the angular speed will be given as the final angular speed, and of which the final angular speed will be given as the final angular speed is equal to the angular acceleration times time plus initial angular speed. So you'll be able to have that. Make sure that you know the concept of the angular should be rotation kinematics, because this concept much uses those as well, of which I understand you know those things. Now let's say this is the question. A torque of 0.97 Newton-meter, that is a torque 0.97 Newton-meter, is applied to a bicycle wheel of radius, that is the radius 35 centimeter, of which has to be in meters. So have 37 times 10 to the power negative 2 meters. Make sure that you know about the prefixes. That we have the mass given as 0.75 kgs. Now what's the question? Which to have the angular acceleration. What is the formula? Torque divided by the moment of inertia. And of which you have mr square, that is force times radius. Now let's see these questions as well. When a ceiling fan rotating with an angular speed of 3.66, that is initial angular speed, that is 3.66 rad, should be rad per second, is turned off, and friction torque, that is a torque, is given as 0.125 Newton-meter, slows to a stop, which means the final angular speed is given as in 31.8 seconds. That is the time. 8 seconds. Now what is the moment of inertia? That is I. Now how should you have the moment of inertia? So in this case, the moment of inertia will not be calculated using its formula. We'll find the moment of inertia using the torque formula. That is given as, we'll have it as, we know that the angular acceleration, it is given as the torque divided by the moment of inertia. Then now we'll make the moment of inertia as the subject. That will be given as moment of inertia is equal to the torque divided by the angular acceleration, of which the torque will have it is using, of which the torque is already been given, of course. Then we should have to calculate the angular acceleration using the equation of the rotation kinematics. Since we have the initial, final as the time, we'll use the formula final is equal to angular acceleration time plus the initial, in that way. Then you'll be able to have it in that case. Now let's have this case as well. Let's say we have the equation when a ceiling fan rotating with angular speed of, that is initial angular speed, we have 3.66 rad per second, is turned off, and a friction torque, that is the torque of 0.125 should be a Newton-meter, slows it to a stop, that is the final angular speed is given as in now we have it as a time 31.8 seconds. what is the actually a moment of inertia of the fan? So now, since we have been given the torque, obviously the moment of inertia will be given as using the formula for actually torque. So try to go through for that, of which you also need to have the angular acceleration. That will be necessary as well. So just have to see, having the initial final time, obviously the angular acceleration will be given using the formula final, using the equation of kinematic, actually rotation kinematics, which is final angular speed is equal to angular acceleration times time plus initial angular speed. You have that. And let's go for the other question as well and see how we can make it up to. And let's say the question says, when the play button is pressed on, actually is pressed, a CD acceleration from rest, that is initial velocity, that is initial velocity 0, and 245 0, that is the final velocity, that is final angular velocity, 45 0 rev per minute, of which you should know how to convert this to rad per second. In 3.0 revolutions, that's the angular displacement, of course, has been given in terms of rev. You should know how to convert this to actually a rad. If the CD has got the radius, now we have the radius 6.0 centimeter, of which has to be in meters as well. It has a mass of, we have the mass of 17 grams, of which has to be in kgs, of course. And what is the torque? Now, a torque should be given using the formula for the actually angular. The torque should be given using the formula for angular acceleration as well as the moment of inertia, since we have been given the mass. So try to see how best you can go for that. So there are a lot of problems you have to go through, and of which you come across them in different books just for you to practice. But that's how you can have the typical recap or the review on the angular acceleration as well as the torque. Thank you.